Hello, my dear friends. How are you? Hope you're fine. What about your studies? Study well. Keep going. Okay. In the previous discussion, we have stopped at the classification based on classification of colloids. Okay. Now we are continuing the classification from the classification based on the particle of the displaced phase. Okay. Without wasting time, we can directly go to the points. Okay, that is classification based on the type of particles of the dispersed phase. In this category, we can classify the colloids mainly into three categories. The first one is multimolecular colloids. What do you mean by multimolecular colloids? Yes, here on dissolution, a large number of atoms or more small ions of a substance aggregate together to form a species having size in the colloidal range. It is multimolecular colloids. Simple. On dissolution, a large number of atoms or smaller molecules of a substance aggregate together to form a species. And its property is what? Its size in the colloidal range. Okay, got the point. And it is multimolecular colloids. An example is gold salt, sulfur salt example. Okay, the example of multimolecular colloids is gold salt, sulfur salt, etc. That is all about multimolecular colloids. Next we can move to macromolecular colloids. Next is macromolecular colloids. As the name indicates, this classification have some relation with macromolecules. Here, macromolecules in suitable solvents to form solution. Okay, macromolecules in suitable solution form solution. What is the property of that solution? In which the size of the macromolecules may be in the colloidal range. Okay, and it is macromolecular colloids. Got the point? Macromolecules in suitable solvents form solution in which the size of the macromolecules may be in the colloidal range. And entities become macromolecular colloids. Okay, what it have one property is that is these are stable, and it have a resemblance to true solution in many respects. Macromolecular colloids are stable and it resembles true solution in many respects. Okay, they have some similarity between solutions. Example for macromolecular colloids are starch, cellulose, proteins, polythene, nylon, etc. Okay, next we can move to the next classification, that is associated colloids or micelles. Associated colloids or micelles. What is that? Yes, the substance which at low concentration behave as normal electrolytes, but at a higher concentration exhibit colloidal behavior due to the formation of aggregates. And these particles are called associated colloids or micelles. Okay, that is, at a low concentration the substance behaves as normal electrolyte. When the concentration increases, what will happen? Yes, it will exhibit colloidal behavior. Why? Due to the formation of aggregates, and it have a size in the range of colloidal. And this type of particles are called associated colloids or micelles. Okay, in the micelle formation or in the aggregate colloids case, we need to understand 2 points. or two, we need to understand some new terms, that is Kraft temperature and critical micelle concentration. What is Kraft temperature? Yes, the temperature at which or above micelle formation take place is the Kraft temperature. The temperature at which or above micelle formation takes place is the Kraft temperature. Got the point? Then what is critical micelle concentration? Yes, that is a concentration at which or above the micelle formation takes place is the critical micelle concentration. The concentration at which or above the micelle formation takes place is called critical micelle concentration. Okay, and examples of these associated colloids or micelles are soap, synthetic detergents, etc. Soap and synthetic detergents are examples of associated colloids. I think the classification based on the type of particles of dispersed phase is clear. That is multimolecular, macromolecular and associated colloids. Okay, next we can study the mechanism of micelle formation. How the micelle formation takes place. Okay, we already says that is soap is an example of associated colloids. So we can check how the soap works. Okay, we know that what is soap? Soap is a sodium or potassium salt of higher fatty acid. Soap is the sodium or potassium salt of higher fatty acids. Okay, what will happen when soap dissolved in water? Yes, when dissolved in water, soap dissolves it to form RCOO minus and Na plus or potassium ion. Okay, sodium or potassium ion. There is RCOO minus part and Na plus ion part. Two part. Soap dissolves it into two part. Here, the RCOO minus part is, we know that R is the organic group. So what will happen? It is non-polar, do not dissolve in water. It is hydrophobic in nature, that is water repelling. Okay, it is a hydrocarbon part and it is water repelling and it is non-polar tail. RCO minus is a non-polar tail part and it is hydrophobic in nature and water repelling. Whereas COO minus is polar ionic head. Okay, where R is the non-polar part and COO minus part is polar ionic head. Okay, and it have a attraction to water as water loving, because what is the case? Yes, it have a charge. It is the polar part. Water has some polar character and this RCO minus also has some polar character. It is hydrophilic water loving part, COO minus. Sodium citrate is an example. Sodium citrate, whereas C17 with 37 is the R part and COO minus is the head or polar ionic head part. Got the point? Okay, then we can check how it works. When the soap dissolves in water, the COO minus group dissolve in water. The COO minus group will dissolve in water and the hydrocarbon tail part will not dissolve. It is move away from water repelling. Okay, at the micelle concentration, a micelle is formed in spherical shape. A micelle is formed in spherical shape, in which the hydrocarbon chain is inside. The hydrocarbon chain is inside and COO minus part is outside. That is, we consider as like a ball, like a football or a cricket ball. That is inside. What is the part? Inside the hydrocarbon part and outside the surface of the ball and the polar part, COO minus part. That is an ionic micelle is formed. This is the case of soap. That is COO minus is present in the case of soap. But in the case of detergent, the polar part is SO4 minus. In the case of detergents, the polar part is or polar group present on the surface of the micelle is SO4 minus. Okay. And the mechanism of micelle formation is same as that of the soap. Got the point? The mechanism is same as that of the soap, but the ionic part is sulfur, SO4 minus. Okay. Now we can check the cleansing action of soap, how the soap works. If oil or grease part is present in our cloth, what will happen? Yes, if we wash the cloth during the washing time, a micelle is formed around the oil or grease part. We already said that micelle is a spherical shape and the inner part contain the non-polar group. That is, a micelle is formed around the grease or oil part in such a way that the oil is inside the ball. So what will happen? The oil or grease part will form bonds with the micelle and it is keep away from water. So it dissolve. The oil or grease part will dissolve in the hydrocarbon part and the outer surface will dissolve in water. Inner surface will dissolve in the hydrocarbon part and the outer surface dissolve in water. So what will happen? The grease or the oil part can be easily removed from the cloth. In this way, the working of detergents, soap take place. Okay. Next we can move to the preparation of colloids. That is preparation of colloids. Okay. The first one is chemical methods. In the chemical methods, we can use oxidation, reduction, hydrolysis or double decomposition for the preparation of colloidal solution. Okay, that is oxidation, reduction, double decomposition or hydrolysis. This method can be used for the preparation of colloidal solution. Okay, this is the first method. That is chemical method. Next we can move to the next method of preparation, that is electrical disintegration or Bredig's arc method. Electrical disintegration method or Bredig's arc method. Okay, what is this method? In this method, an electric arc is produced between two electrodes, which is immersed in the dispersion medium. That is, an electric arc is produced in the dispersion medium using the electrode. And during the electric struck, what will happen? Intense heat is produced, and this will lead to the vaporization of metal, which then condenses to form colloidal particles. Okay, once again, in this method, an electric arc is produced between the two electrodes immersed in the dispersion medium. The intense heat produced leads to the vaporization of the metal, which condenses to form colloidal particle. Okay, that is what are the processes taking place? That is a dispersion and a condensation. A dispersion and condensation occurs here. Okay, an example is the preparation of gold, silver, platinum colloids. The preparation of gold, silver, platinum colloids can be prepared using this method. You may please refer the textbook for the figure. Due to some problems of copyright, I cannot include the photos. You may please check the figure showing the textbook. So it is all about electrical disintegration or Bredig's arc method. Okay, Next we can move to the another preparation, that is peptization. In this process, a precipitate is converted into a colloidal salt. In peptization, a precipitate is converted into a colloidal salt. How? Here, the precipitate is taken in dispersion medium in the presence of small amount of electrolyte and shaken well. It leads to the formation of the production of salt. Got the point? That is, the precipitate is taken in a dispersion medium in the presence of small amount of electrolyte and shaken well. The whole is taken in a beaker or vessel and shaken well. It leads to the production of salt. Okay, and the electrolyte used is called as peptizing agent. The electrolyte used is called the peptizing agent. It is a case of peptization reaction. It is a preparation using peptization. Here, a salt, colloidal salt, is prepared from a precipitate. Colloidal salt is prepared from a precipitate with using dispersion medium, some amount of electrolyte, that is the peptizing agent. This is a simple process. Okay. Then we can next move to the next topic, that is purification of colloidal solution. Next topic is that purification of colloidal solution. When the colloidal solutions are prepared, it is usual that it contain unnecessary impurities. So we need to reduce the concentration of soluble impurities to a minimum value. We need to reduce the concentration of impurities to a minimum value. So the process of reducing the impurities to a minimum is known as purification of colloidal solution. The process of reducing impurities in a colloidal solution, colloidal solution, that is freshly prepared colloidal solution, to a minimum value, is called the purification of colloidal solution. There are mainly three methods are used for the purification. There are mainly three methods. What are they? First, dialysis. Second, electrodialysis. Third, ultrafiltration. First, dialysis. Second, electrodialysis. And third, ultrafiltration. That we can check one by one. The first method is dialysis. In dialysis, the removing is carried out using a membrane, using a suitable membrane. We know that through membrane, the particles in a solution can move. That is, we studied that osmosis, this semi-permeable membrane and its properties. Like that, when we take a membrane, the particles of solution can pass through the membrane, whereas the colloidal particles cannot pass through it. So this speciality is using here. The speciality of a membrane to pass or allow the passage of solution particles and preventing the passage of colloidal particles is using here in dialysis. Okay, for this we using an apparatus called a dialyzer. Using the apparatus called dialyzer. In here, we using the method is the colloidal solution that we need to purify is taken in a membrane bag. In a membrane bag, that is, it can allow the passage of particles of solution and prevent the passage of colloidal. So the solution is taken in a membrane bag and is suspended in a vessel in which fresh water is continuously flowing. So what will happen? Yes, the particles from the solution moves to the fresh water and the colloidal particles will left behind. Okay, the clear picture is given in the textbook. You may please refer. Okay, it is the case of dialysis. What the point? Next we can move to electrodialysis. Next is electrodialysis. In electrodialysis, it is a sophisticated or it's a most modern form of dialysis. In electrodialysis, what will happen? In electrodialysis, we overcome the drawback of dialysis, the conventional dialysis. The conventional dialysis, the process is slow. In conventional dialysis, the process is, ordinary dialysis is very slow process. So, the dialysis can be made faster by applying an electric field. Then this process is called electrodialysis. The arrangement of electrodialysis is same as the case of dialysis. The arrangement of dialysis is same as the case of arrangement of electrodialysis is same as the case of dialysis. There is an additional introduction of electrodes in electrodialysis. That is for what? Yes, when the electrodes are arranged in such a way that oppositely charge is applying to complete the circuit. So what will happen? Then the ions present in the solution with opposite charge will move to these electrodes. The ions present in the solution will move to the oppositely charged electrodes. In this way, the electrodialysis is taking place. So, this is the case of electrodialysis. This is clear that electrodialysis is more faster than dialysis. Okay. Next purification process is ultrafiltration. Next purification process is ultrafiltration. Here, we using a filter, that is a specially prepared filter for the purification or the separation. How? Yes, here what will happen? The property of the specially designed filter have a property that it permeable to all substances except colloidal particles. That is, it allows the passage of all particles except the colloidal particles. Okay, this method can be used for the separation of colloidal particles from the solvent and soluble electrolytes. But the process is a slow process. Ultrafiltration is a slow process. So we need to apply a pressure or suction to increase the speed. Okay, to increase the speed of the rate of the reaction, what will we do? Yes, we need to apply pressure or suction. Then at the end, the colloidal particles are left on the filter paper, and then it is stirred with the fresh water and gives the pure colloidal solution. Okay, it is also a simple process. So the purification is mainly dialysis, electrodialysis and ultrafiltration. Okay, these are the cases of purification. Got the point? Next, we can discuss the properties of colloidal solution. Now we are going to discuss the properties of colloidal solution. The first property is colligative property. We already studied that colligative property is the properties which depends on the number of particles. Okay, so here also we know that colloidal particles are also there is a particles, so the number. So the colligative property, how colligative property is applicable to these colloids, we can discuss. We know that colloidal particles are high molecular mass particles. So what will happen? The number of particles in colloidal solution is comparatively small if we take a unit volume. Due to the high molecular mass, the number of particles in unit volume is small. So what is the case? Then the value of colligative property is also small. Number of particles is small. What will happen? The colligative properties of colloidal solution is also small. That is the case of colligative property of colloidal solution. Next we can discuss another important point, that is Tyndall effect. Very important point, as an exam point of view, it is very important. Tyndall effect. What is the relation between Tyndall effect and colloidal solution? We can check. The Tyndall effect is an optical effect. Tyndall effect is an optical effect, and it is due to the fact that colloidal particles scatter the light in all directions in space. Colloidal particles scatter the light in all directions in space, and this scattering of light will illuminate the path of the beam. Tyndall effect is an optical effect, and the colloidal particles scatter the light in all directions in space, and this scattering of light will illuminate the path of the beam. And for the observation of Tyndall effect, two conditions should be satisfied. For the observation of Tyndall effects, two conditions need to be satisfied. What are the conditions? Yes, the first one is the diameter of the dispersed particle. The diameter of the dispersed particle is not much smaller than the wavelength of light used. The diameter of the dispersed particle is not much smaller than the wavelength of light used. That is the relation between diameter of the dispersed particle and wavelength. That is, wavelength should be approximately, or should be very close to the diameter of dispersed particle. Okay, the next point, the next condition is that there should be a great difference in the magnitude of refractive indices between dispersed phase and dispersion medium. That is, a great difference should be there. We need a great difference in magnitude of refractive indices between the dispersed phase and dispersion medium. Okay, these are the two conditions that should be satisfied to observe the Tyndall effect. Next we can move to another point, that is how it is used. Tyndall effect can be used for the distinguish between colloidal and true solution. Colloidal and true solution can be distinguished using Tyndall effect. Okay, another point is that the principle of Tyndall effect is used for the construction of ultramicroscope. The principle of Tyndall effect is used in the construction or working of ultramicroscope. What's the point? Okay, it is the case of Tyndall effect and colloidal solution. Next we can check the color of colloidal particles. What is the color of colloidal solution? The color of the colloidal solution depends on the wavelength of light scattered by the dispersed particles. The color of the colloidal solution depends on the wavelength of light scattered by the dispersed particles, and it also depends on the color. The color also depends on the manner in which the observer receives the light. So the color depends on the two factors, that is the wavelength of light scattered by the dispersed particle and the observer, and the manner in which the observer receives the light. Okay, we can take some example. If the mixture of milk and water is taken, it appears as blue when the observer sees the reflected light. Mixture of milk and water appears blue when viewed by the reflected light, and the same mixture appears as red color for the transmitted light. The same mixture observed red color for transmitted light. This is a difference. Next we can move to another example for the gold sol. What is the case of gold sol? It actually appears in a red color. But when the size of the particles increases, when the size of the gold sol, the particles in gold sol increases, the color changes to purple. Okay, that is red to purple. The changes is finally leads to the formation of golden color. This change, red, purple, and finally leads to golden color. Okay, this is a change. So it is the case of color and colloidal solution. Got the point? Okay. Next we can discuss the Brownian movement of colloidal particles. What is the relation between Brownian movement and colloidal solution? What is Brownian movement? Okay, when a colloidal solution is observed with an ultra microscope, it can be seen that the colloidal particles are in a state of zigzag motion, and this motion is called Brownian movement. Okay, when a colloidal solution is observed with an ultra microscope, the colloidal particles are in a state of zigzag motion. This movement is called Brownian movement. I think it was clear. So the Brownian movement depends on the size of the particle, viscosity of the solution. Brownian movement depends on size of the particles, viscosity of the solution. And the Brownian movement is independent of nature of colloids. Very important. Brownian movement is independent of the nature of colloids. Brownian movement depends only on the size of the particles and viscosity of solution. Okay, then what will happen if size and viscosity, what is the change? If smaller the size and lesser the viscosity of the solution, then the Brownian movement will be faster. What is? If smaller the size and lesser the viscosity, then the Brownian movement will be faster. The Brownian movement can be explained using the concept of unbalanced bombardment of the particles by the molecules of dispersion medium. That is, a Brownian movement occur by the bombardment of what? Particles of the molecules of dispersion medium with collision. This leads to the formation of Brownian movement. I think it was clear. That is only a zigzag movement of the colloidal particle leads to the formation of Brownian movement. So exam point of view is very important, Brownian movement. So study well. Okay. Next we can move to the charge on colloidal particles. The next topic is charge on colloidal particles. How the colloidal particles and relate with the charge. We can check. The colloidal particles always carry an electrical charge. Very important point. The colloidal particles always carry an electrical charge. The nature of the charge of colloidal particle is the same on all particles in a given colloidal solution. Can be positive charged or negatively charged. Colloidal particles have a charge, and in a colloidal solution, this charge is same for all colloidal particles. It can be positively charged colloidal solution or negatively charged colloidal solution. If we consider some example, positively charged salts. The examples of positively charged salts are hydrated metallic oxides of aluminium, hydrated metallic oxides of chromium or iron, etc. Hydrated metallic oxides of aluminium, chromium, iron, etc. are examples of positively charged colloids. If we consider the case of negatively charged colloids, metallic sulfides of arsenic, antimony, cadmium, etc. are examples of negatively charged colloids. Metallic sulfides of arsenic, antimony, cadmium are examples of negatively charged colloids. These are positively charged colloids and negatively charged colloids. Okay. These small particles, how these particles got the charge, how they become negative or positive. The positive or negatively charged colloidal solutions are formed by the preferential adsorption. So we need to study what is preferential adsorption. Here it is simple. We can consider an example. By using an example, we can discuss the preferential adsorption. In preferential adsorption, if we consider the case of silver nitrate and potassium iodide solution, if we add silver nitrate to potassium iodide or potassium iodide to silver nitrate, what will happen? It will lead to the formation of silver iodide. We know that. If potassium iodide is added to silver nitrate or silver nitrate is added to potassium iodide, it leads to the formation of the product silver iodide. Then where is the differential adsorption? We can check. If silver nitrate is added to potassium iodide solution, we already said silver iodide will formed. Then what will happen? Yes, this silver iodide formed adsorb iodine from the dispersion medium. Got the point? Silver iodide formed will adsorb iodine from the medium. That is, we added silver nitrate to potassium iodide solution. So enough iodine molecules are present, it will adsorb silver iodide from the solution. Okay, in this way negatively charged, that is I minus potassium iodide, it is negatively charged. So negatively charged colloidal solution will form. In the same way, if we add potassium iodide solution to silver nitrate, potassium iodide solution to silver nitrate, there is in silver nitrate solution there is large amount of silver ion and nitrate ions are present. So what will happen? Potassium iodide is added to silver nitrate. Yes, silver iodide is formed, and the positively charged Ag plus will, the silver iodide formed will adsorb the positively charged silver ion. Got the point? In this way, potassium iodide positively silver iodide positively charged and silver iodide negatively charged colloid particles are produced. Got the point? Next we can take another example, that is in the case of FeCl3, ferric chloride. What is in the case of ferric chloride? In the case of FeCl3 is added to excess of hot water, positively charged sol are produced. If FeCl3 is added to excess of hot water, positively charged colloidal particles are produced. If FeCl3 is added to NaOH, negatively charged colloidal particles are produced. If FeCl3 is added to NaOH, negatively charged colloidal particles are produced. Got the point? It is the process of preferential adsorption. We already said that a positive or negatively charged colloidal solution can be prepared by selective adsorption. And the layer which formed on the surface of this colloidal particle will attract the counter ion from the medium. That is, we already said that in the medium there is excess of ions. So the first layer formed and the first ion have a charge it will attract its counter ion to form the second layer. Got the point? So what will happen? A second layer also will be formed. A second layer also will be formed. The combination of the two layers of opposite charge around the colloidal particles is called Helmholtz electrical double layer. The combination of two layers of opposite charge around the colloidal particle is called Helmholtz electrical double layer. It is very important. The first layer of ions is firmly, that is the first layer. The first layer is firmly held and is termed as fixed layer. The first layer formed is firmly attracted the colloid, so it is very strongly bonded to the surface, so it is called a fixed layer. And the second layer of ions is mobile. It is only an attraction. So the second layer of ions is mobile, which is termed as diffuse layer. The first layer is fixed layer and the second layer is diffuse layer. And the potential difference, there is a potential, we know that there is a opposite charge. The first layer is if positive, the second layer is negative. If first layer is negative, the second layer is positive. There is a potential difference. The potential difference between the fixed layer and the diffuse layer is called zeta potential or electrokinetic potential. The potential difference between the fixed layer and the diffuse layer is called the zeta potential or electrokinetic potential. Got the point? Okay. That is, we already discussed that the colloidal particles have a charge and it is same for all particles in that colloidal solution. And the presence of equal and similar charge on the colloidal particles is largely responsible for the stability of the colloidal solution. The presence of equal and similar charge on the colloidal particle is responsible in providing the stability to the colloidal solution. Okay, how? Because due to this repulsion between the same charge, the repulsion between the same charged colloidal particles prevent them from forming aggregation when they come closer. Due to the same charge, they will repel and it prevent them from aggregation. So in this way, the stability of the colloidal solution is maintained. Got the point? The stability of the colloidal solution is maintained. Okay. Next we can study what is electrophoresis. What is electrophoresis? What is electrophoresis and what is the relation between electrophoresis and colloidal solution? Do you have any idea? Okay, we can see what is the relation. When an electric potential is applied across the two platinum electrode which is dipped in a colloidal solution, what will happen? Yes, the colloidal particles will move to electrodes. The negative ion will move to anode and positive ion move to cathode. Then the movement of colloidal particles under an applied electric potential is called electrophoresis. The movement of colloidal particles under an applied electric potential is called electrophoresis. Okay, that is the movement of colloidal particles under an applied electric potential. It is electrophoresis. If we prevent the movement of the particles in an electric field, the movement of the particles in an electric field, then what will happen? Then we can see that the dispersion medium begin to move. Okay, if we prevent the particles, the movement of particles, then we can see that the dispersion medium began to move under the electric field, and it is called electroosmosis. If we prevent the movement of the particles, then the dispersion medium began to move, and it is called electroosmosis. And here electrophoresis and electroosmosis. Okay, got the point. Next we can discuss the coagulation or precipitation of colloids. That is coagulation or precipitation of colloids. We said that the stability of the sol or the colloidal particle is due to the presence of the charge on the colloidal particles. That is, the stability of colloidal particles is due to the charge. So what will happen if the charge is removed? Yes, it will aggregate or precipitate and will settle down. The process of the precipitation or the setting down of colloidal particles is called the coagulation of the sol or the precipitation of sol. The process of setting of colloidal particles is called the coagulation or precipitation of sol. Okay, this precipitation or coagulation of the sol or the colloidal particles can be in different ways. The charge can be removed in different ways. So we can take one by one. The first one is that by electrophoresis. We already discussed what is electrophoresis. So in electrophoresis, how it is applicable for coagulation, how it leads to coagulation, we can see. We said that the colloidal particles are moved to oppositely charged electrodes. Then what will happen? By the movement, when they attach to the electrode, they will be discharged and the colloidal particle will be precipitated. The colloidal particle moved to oppositely charged electrode and discharged at the electrode and the colloidal particles will be precipitated. And the next is by mixing of two oppositely charged sol. That is taking a positive and negative. This will lead to the neutralization of charges. If we mix two oppositely charged colloid solution, this leads to the neutralization of charge and it will be precipitated partially or completely. A complete or partial precipitation is occur when oppositely charged sols are mixed. And this mixing type precipitation is also called mutual coagulation. This type of coagulation is also called mutual coagulation. Got the point? That is by electrophoresis and by mixing. The next method of precipitation is by boiling. By boiling. How boiling leads to the formation of precipitate? When sol is boiled, the adsorbed layer is disturbed. When the sol is boiled, the adsorbed layer becomes disturbed. Why? Because the collisions increase within the molecules. That is, when the sol is boiled, the adsorbed layer is disturbed due to increased collision with the molecules of dispersed medium. Then what will happen? This increased collision will reduce the charge on the particles. This increased collisions will reduce the charge on the particles and ultimately lead to the settling of sol. Okay, this is due by using boiling the temperature. Okay, it leads to increase in collision and reduces the charge. That is a removing of charge by increasing the collision. That is the case of boiling. The next way to precipitate is by persistent dialysis. By persistent dialysis. In this process, after a prolonged dialysis, the traces of electrolyte present in the sol are removed completely. That is the total removal of electrolyte. After prolonged dialysis, the electrolyte is removed completely. Then it will leads to the coagulation. because the colloidal particle will become unstable and it will lead to coagulation of the colloidal particles. So by persistent dialysis leads to the formation of precipitation of colloidal particles. Okay. In the same way, the addition of excess electrolyte also can lead to the formation of the coagulation of colloids. That is the next point is that by the addition of electrolyte, how the addition of electrolyte leads to the coagulation of colloids. When excess electrolyte is added, the colloidal particle will precipitate. When excess electrolyte is added, the colloidal particle will precipitate. How? Because the interaction of colloid with oppositely charged particle increases and leads to the what will lead to? It leads to the coagulation. Okay, when excess of electrolyte is added, what will happen? The interaction between oppositely charged particle increases. If a negative ion is present in the electrolyte, it will lead to the precipitation of a positively charged salt. And if a positively charged ion is present, it leads to the precipitation of negatively charged salt. Okay, but if we can see that excess of electrolyte leads to the formation of colloids, and also the complete removal is also due to the formation of colloids. Complete removal of electrolyte also leads to the formation of colloids. Okay. Here we need to study a rule which connect the precipitation using electrolyte and the precipitation of electrolyte using the electrolyte. A rule which connect the precipitation of colloids using electrolyte. That is Hardy-Schulz rule. Hardy-Schulz rule. Hardy-Schulz rule states that if greater the valence of the fluctuating ion, it states that if greater the valence of the fluctuating ion, the greater is its power to cause the precipitation. If greater the valence of the fluctuating ion added, the greater is its power to cause precipitation. That is, if we consider the coagulation of a negative salt. If we consider the case of the coagulation of a negative salt, the fluctuating power is in the order Al3 plus greater than Ba barium 2 plus greater than sodium plus. That is 3 plus 2 plus plus. That is the 3 plus have the highest value for coagulation than 2 plus than plus. That is, greater the valence of the fluctuating ion added, the greater is its power to cause precipitation. Got the point? And in the same manner, if we coagulate a positive salt, then the fluctuating power can be, what will happen? Yes, it is also in the same manner. FeCN6 4 minus greater than PO4 3 minus greater than SO4 2 minus greater than Cl minus. That is 4 minus is greater than 3 minus, and which is greater than 2 minus, and it is greater than minus. So very important, Hardy-Schulz rule, connecting the relation between the electrolyte and the precipitation. It states that greater the valence of the fluctuating ion added, greater is its power to cause precipitation. Here we need to understand a term called coagulating value. What is meant by coagulating value? It is the minimum concentration of an electrolyte in millimoles per liter. Minimum concentration of an electrolyte in millimoles per liter required to cause precipitation of a salt in 2 hours. That is, the minimum concentration of electrolyte needed to cause precipitation in 2 hours is called coagulating value. That is, we need to consider 2-3 factors, that is concentration of electrolyte in millimoles per liter, precipitation 2 hours. That is coagulating value. Coagulating value is the concentration of an electrolyte in millimoles per liter required to cause precipitation of a salt in 2 hours is called coagulating value. Okay, smaller the quantity needed, higher will be the coagulating power of an ion. Okay, if it need small quantity of a small concentration is needed, what will the case? That is, higher will be the coagulating power of an ion. That is the case of coagulating value. That is, study well. Okay. Next we can check the coagulation of lyophilic salts. How we can coagulate lyophilic salts. Okay, we already seen that the charge and the solvation of colloidal particles are the two factors which are responsible for the stability of lyophilic salts. Okay, that is the charge and solvation of colloidal particles. What will happen if these factors are removed? By removing these factors, lyophilic salt can also be coagulated. Okay, charge and solvation of colloidal particles. By removing these factors, lyophilic salt can also be coagulated. How we can coagulate? By adding an electrolyte or by adding a suitable solvent. The salt can be coagulated. Okay, by changing the stability factor, the salt can be, lyophilic salt also can be coagulated. Got the point? Next we are going to study an interesting topic, that is protection colloids. That is protection of colloids. Lyophilic salts are more stable than lyophobic salts. Lyophilic salts are more stable than lyophobic salts because lyophobic colloids are extensively solvated. Okay, and lyophilic colloids have a unique property of protecting lyophobic colloids. Lyophilic colloids have a unique property of protecting lyophobic colloids. How it is work? When a lyophilic salt is added to a lyophobic salt, the lyophilic particles form a layer around the lyophobic particles. Okay, and thus protect the latter from the electrolytes. If we add lyophilic to lyophobic, the lyophilic will form a layer around the lyophobic and it will protect lyophobic from the electrolytes. Okay, and the lyophilic colloids used for this purpose are called protective colloids. Lyophilic colloids used for this purpose are called protective colloids. Okay, that is a kind of love, we can say a kind of love between lyophilic and lyophobic. Okay, next we can study what is emulsion. What is emulsion? Emulsion is a liquid colloidal system. Emulsion is a liquid colloidal system. Okay, if a mixture of two immiscible or partially miscible liquid is shaken, what will happen? We get one liquid is partially dissolved in another and we obtain an emulsion. That is, a liquid colloidal system is called a emulsion. Okay, there are mainly two types of emulsion, that is oil dispersed in water emulsion and water dispersed in oil emulsion. Water dispersed in oil emulsion and oil dispersed in water emulsion. In oil dispersed in water emulsion, water is the dispersion medium. In oil dispersed in water, the water is the dispersion medium. An example is milk. Okay, and it is unstable and it forms two layers. Okay, it forms two layers, oil in water type. Okay, oil dispersed in water. Here water is the dispersion medium, milk is an example, and it is unstable and form two layers. Okay, and in the case of water dispersed in oil, oil is the dispersion medium. If water dispersed in oil is act as the dispersion medium. Butter, cream are example. Okay, here we need to understand a new term, that is emulsifying agent. Emulsifying agent. What is emulsifying agent? Emulsifying agent form an interfacial film between the suspended particles and the medium. Emulsifying agent, it forms an interfacial film between the suspended particles and the medium. Okay, in the case of oil dispersed in water, the emulsifying agents are soap, proteins, gums, etc. That is, in water, the emulsifying agent are soap, protein, gums. Okay, in the case of water dispersed in oil, the emulsifying agents are long chain alcohol, lamp black, heavy metal salts of fatty acid, etc. Okay, this is the case of oil dispersed in water and water dispersed in oil, emulsifying agent. That is for the improving or increasing the solubility of the dispersed phase in the dispersion medium. Okay, here in emulsion, the dispersion phase and dispersion medium are liquids. Okay, the emulsion can be broken into constituent liquid by using freezing or centrifuging or heating. By using any of this method, we can take back the constituent particles in an emulsion. Okay, next we can go to a small look of colloids around us. That is, most of the substance we are using in our daily life are colloids. Most of the substance we are using in our daily life are colloids. Food items, clothes, wooden furniture, etc. are examples of colloidal substances. And the colloidal particles have a role in the blue color of the sky and fog, mist, rain formation, and in the blood, soil, formation of delta. In all these items, there is a role of colloids. So, in our day-to-day life, most of the substances we have used have a role of colloids. Okay, and these are the natural phenomena that is using the properties of colloids. Let we can move to the applications of colloids. Yes, that is in electrical precipitation of smoke. The application of colloid is used in the electrical precipitation of smoke, and purification of drinking water, and in medicine industry, in tanning, cleaning action of soap, photographic plate and films, and rubber industry, and industrial products like paints, ink, and cements. These are examples of colloidal, and in all these and many more is remaining. These are some examples of applications of colloids. So this is not a theoretical concept, but it is a practical evident the role of colloid. So today we are winding up this video. So this is the last portion of this chapter, surface chemistry. You may please study well. If you have any doubts, you may please clarify with your teacher, because in my whole class I say that you may please clarify with your teacher, because the clarification should be more clear. If you ask me, I am ready to answer your questions, but there is a limitation. So if you clarify your doubts with your teacher, it is very helpful for you because it is a direct clarifying. Because sometimes you may ask to me, I may miss your question, so you cannot I cannot answer your questions. So if you clarify with your teacher, you can directly get the answer. So because of this reason, I always says that you may please clarify with your teacher. I am again repeating. You may please clarify. Don't, if you have any doubts, you may please clarify with the teacher and study well. And thank you for watching. Thank you.